Hey, Physics 20s, it's Mr. Jukely here. Going to talk to you about conservation of energy. So it's kind of a continuation of the last lesson that we did, except now we're adding some of the mathy pieces to it. So we're looking primarily at lesson 5 today. That's our conservation of mechanical energy, and that is an essential piece of what we're actually looking at in Physics 20 that's really going to help us out with Physics 30. And then the more on the enrichment side of things, we're going to look at our conservation of energy with work. That's lesson 6, and I'm just going to add it in here. We're going to do a very quick version of it, and if you don't want to check that one out, that's okay. We need to do lesson 5. You might want to do lesson 6. Okay, let's jump into it. So, if we have conservation of mechanical energy, that means that our system is indeed conservative. So we have a conservative system, and that's something, again, that's pretty important for Physics 30. The fact that no energy is being added and no energy is being lost from the system, or in other words, our mechanical energy stays the same. Our mechanical energy stays constant. And another way we could look at this, no energy is added, no energy is lost. So, and things that would add energy are like electric and gas motors. Things that would take energy out of the system are like heat, sound, friction, things like that. Cool. So if you just take a moment to check out the animation up here, the little cart starts way up here at the top, and then it falls down, falls down, falls down, and then goes up the loop, and things that we can look at as we go down. So as we start from the very, very beginning, we had lots and lots and lots of, we'll wait till it starts over again. It's kind of a slow, annoying thing, but we'll give it a second till it starts over. Almost, almost, almost. So we're starting at the top with lots of potential energy. And then as it falls down, the potential energy decreases and the kinetic energy increases. And then as it goes up, the kinetic energy decreases and the potential energy increases, and so on and so on and so on. So they're switching back and forth. That's an energy transformation from one thing to another. But TME, that's not how we really abbreviate it in our classroom. That's total mechanical energy. You'll notice stays exactly the same. There is a conservative system right there. We can change energies within the system, but the total mechanical energy for the entire system has to stay the same. So another way that we could potentially look at this is that we could talk about only conservative forces are acting on the system. So conservative forces are things like force of gravity and spring force. They're also kind of like recoverable, so you can get the energy back from them. So you lift something or you throw something up to a particular height. Well, yes, the force's gravity is acting on it. That force of gravity can put the energy back into the system in terms of like kinetic energy. So cool, conservative systems have conservative forces. And again, the ones that we're going to look at, force of gravity and spring force. So again, same sort of thing. You know, we've got force of gravity that we're acting against, bringing the ball up to the top. That force of gravity can put the kinetic energy back into the system. Or I've got kinetic energy over here going to spring potential energy over here. There's a large spring force which can put the kinetic energy back in the system, right? So we can get that kinetic energy back. Non-conservative forces are ones that we can't really get back. So I've got this hockey puck, it's sliding at a speed v. There is force of friction that is doing work on this, and it is taking energy. So the work is taking energy out of the system. Once that hockey puck comes to rest, well, it's not going to move anymore unless somebody like hits it with a hockey stick or something, right? It's not going to come back all on its own. Cool. So just one thing to think about here, which situation would be considered conservative? So situation 1, where a tennis ball is lifted up at a constant speed, or situation number 2, where a toy car gains speed as it goes downhill. Only one of these two situations is going to be conservative, right? So let's think about that. Mechanical energy has to be conserved. So let's think about my initial, I'm going to say is at the bottom, and my final is at the top. So this ball is moving at a constant speed. I just randomly chose 5 meters per second. So initial, we've obviously got some kinetic energy, right? Because it's moving, things are moving. I know it's got kinetic energy. That's all I've got initially, especially if I call this a height of 0. 0 height means 0 gravitational potential energy. But then on the final side of things, when it's at the top there, it's still moving at the exact same speed, so it's got the exact same amount of kinetic energy, but now it's also got gravitational potential energy. Are those two things going to be the same? Not really, so our total initial energy is not going to be the same, as our final energy. Therefore, this is a non-conservative system, so not conservative. Not conservative. Cool. So the energy that we're starting with is not the same in the tennis ball as the energy that we're finishing with, non-conservative. So then you probably already picked out, this one is going to be conservative. So at the top, we've got EPG, or at least could be conservative. At the bottom, we've got kinetic energy. And if I had, say, 5 joules of gravitational potential energy at the top, and at the bottom, I've still got 5 joules of energy, it's just kinetic now. This would be conservative because our total initial energy is equal to our total final energy. So this one is, or at least could be, conservative. Now we're forgetting about something here, right? When a cart rolls down a hill, realistically there's friction. If there was friction, this would not be a conservative system, and the 5 joules at the top would not equal the amount of energy we'd have less at the bottom. Cool. But if we assume that there are only conservative forces, so there's no friction and there's no applied force, this one could be considered a conservative system. Cool. So what we're actually going to do right now is we are going to build our formula for our conservation of energy. So when mechanical energy is conserved, the total energy remains constant. Cool. Or in other words, energy can't be created or destroyed, only turned from one form to another. Now, if I wanted to make a formula out of this, I would say that my total initial energy has to equal my total final energy. So no matter what it is, what type it is, what I've got, the total amount in the beginning has to be equal to the total amount in the end. Now we can expand on this. So in the beginning, I might have some gravitational potential energy. I might have some kinetic energy, and I might have some spring energy. Although we, for this class, are not really dealing with spring energy. I'm going to put that one in brackets because we probably won't use that very much unless you're doing the extensions or enrichment. Cool. And then afterwards, I might have a different amount of gravitational potential energy and a different amount of kinetic energy. And possibly, again, I'll put this one in brackets, so maybe a different amount of spring energy. Cool. Now this is just showing, like when we've got this, the ETI is equal to ETF. That's what we want to start with every single one of these questions, every single question, because that's saying that our law of conservation of energy is holding true. So our total initial energy is equal to our total final energy. When we expand it out, we don't necessarily need to show every type of energy that could be there. We only really want to list the types of energy that we have initially and the types of energy that we have in the end or finally. Right? The rest, if it's not there, why list it, kind of thing, right? But this is just showing what we have before has to be equal to what we have after. This is what we could potentially have before and what we could have after. And note that each of the numbers might be different, right? And maybe I could do a real quick example. If I had 5 joules of gravitational plus 6 joules of kinetic plus 3 joules of spring energy, then in the end, I might have 9 joules of gravitational potential plus, let's say, I don't know, 5 joules of kinetic and 0 joules, I don't know why I started put units there, 0 joules of spring potential. But it still needs to equal the same thing. So 14 joules has to equal 14 joules, even though they come from different places, right? The different energies come from different places. Cool. So I think we let's skip over this, I think, and let's jump into just this little idea here. The total energy change must be equal to 0. So in other words, what we're saying is when one type of energy increases, the other type of energy needs to decrease by the same amount. So the total energy change in the system has to be equal to 0. And we just said 14 joules is equal to 14 joules. Neither the initial or the final overall changed when all is said and done. Cool. So another way to potentially look at things. Let's check out an example here. Let's check out one or two quick examples with this. So the mass on the end of a 1.8 meter long pendulum has a speed of 3.75 meters per second. Cool. Determine its maximum height. So let's think about this, and let's just call, just for the sake of this example, let's call this initial. So everything at the top is initial, and everything at the bottom is final. Cool. So if I'm dealing with my law of conservation of energy, and if that law of conservation of energy is holding true, we could start with our total initial energy is equal to our total amount of final energy. So then I think to myself, okay, initially, what's the only type of energy that I have? So if it's at its maximum height, does it have any speed? Remember from unit 1, I believe it was, or maybe it was unit 2, we talked at the maximum height, there is no maximum speed. So VI is equal to 0. Now, if VI is equal to 0, do we have any kinetic energy? No speed means no kinetic energy. So what do we have at the maximum height? So at this particular height, well, if we've got height, we've got gravitational potential energy. So initially, I'm going to say EPGI, and that's all we've got. There's not springs involved with this whatsoever, so why would we include springs? Okay, cool. So we're starting with gravitational potential, and then the pendulum is going to swing downwards to the bottom. And a pendulum is just a mass, by the way. If you don't know this, it's a mass on the end of a string that just swings back and forth and back and forth and back and forth. So at the bottom, if it's at its minimum height, so what we call a height equal to 0 in this case, it doesn't have any gravitational potential. So all that gravitational potential at the top had to turn into a different type of energy. And if it's moving really, really quickly, it's turned into kinetic energy. So our gravitational potential that we're starting with is equal to our kinetic energy that we're ending up with. All right, we have now built our formula. This is our formula for this question. And it's going to be different for other questions. But now what we can do is we can expand on this. And all we're really doing is expanding downwards. So gravitational potential energy, well, that was mgh, and that's on the left-hand side of my equation. And I'm going to say hi, just to be very specific. hf is 0, and we don't need to deal with that very much. On the right-hand side of the equation, we've got 0.5 mv f squared. Now we might start to look at this and we might start to get real frustrated because we don't know the mass. Nowhere in the question does it tell us the mass. Shoot. Well, let's go through and let's rearrange. Like next step's going to be rearrange. So I'm looking for my height. I'm multiplying it by g and h. So that means I need to divide both sides, dividing by m and g. Divide both sides by m and g. And then look what happens. Mass divided by mass cancels. Gravity divided by gravity, it cancels. And on the other side, I've also got mass divided by mass, so it canceled. Did I even need that mass? Not really, right? It cancels out, and we'll see that it's going to cancel out time and time again here. So let's go through and let's just have a quick look. Hi is going to be equal to 0.5 times Vf squared divided by g. I think we have all the information we need there. We just need to plug in some numbers. So that's 0.5 times 3.75 meters per second squared. Please don't forget to squared. Common mistake, but an annoying one nonetheless. And then divided by 9.81 meters per second squared. And you'll notice that squared inside of the brackets is for units, and squared outside of the brackets is for actually squaring, actually doing. All right, just need to put that on pause there to plug the numbers in and get an answer. I'd recommend you do the same thing. And as we finish up, we're going to end up with, okay, with sig digs, I think we need 3 sig digs, 0.717 meters, or 71.7 centimeters. Cool. So there's our first one. If we wanted to do a quick recap, we are always going to start with ETI is equal to ETF. We need to then build our formula. and building our formula is really thinking about what type or types of energy am I starting with and what do I have in the end. Once we build our formula, we can rearrange that formula, plug in some numbers, and solve. One little trick with this one is lots of times we don't actually need mass. It's only actually if we're using spring energy that we're going to end up needing mass, which again is one of those extensions for us. Cool. So let's, that's some space to work. Let's check out one more example. This one gets a little bit bigger and a little bit more complicated. So we want to figure out the speed of the roller coaster at C. Okay, so we got A on the left-hand side. We've got a speed and a height. We've got B, where we've only got a height. And then we've got C, where we're given a height and we're asked to find the speed. Okay, so do I know the total energy at B? I know the height, so I could figure out my gravitational, but do I have any idea about the speed at B? Not really. So I might just skip over B, and I know that I can skip over B because if this is a conservative system, is any energy going to be lost? No. So the total energy at A is going to equal the total energy at B, which is also going to equal the total energy at C. So I'm just going to skip over B. It's going to be the same everywhere. So as I go through and as I start to build my formula, oh shoot, I got it all solved for myself there. Didn't plan out my space very well. Oh well, we'll go down here. I'll just have to scroll up to get the numbers. So I'm going to go through and I'm going to start at the beginning with ETI is equal to ETF. Just my law of conservation of energy in a formula. So my total initial energy is equal to my total final energy. And remember, we're just looking at A and C. We're skipping over the middle piece. We're skipping over B. So if I look at A and I'm looking at my initial side of the equal sign, I've got speed, so I know I have kinetic, and I've got height, so I know I've got gravitational. Cool, okay, so let's go through and let's say EPG initial plus EK initial. So those should be my only two types of energy I have on my initial side of the equal sign. Cool. What about on the other side, on the right hand or the final side of my equal sign? Again, we're skipping over the middle. So at part C, I've obviously got a height. It's a different height, so I'm going to have a different amount of gravitational potential energy. So EPG, and we'll call that EPGF. And the question is asking us for the speed at part C. So that's going to be the kinetic energy at C, which I'll call EKF. Again, it's going to be a different amount. Right, so it's losing some of its gravitational and some of its gravitational is turning into kinetic. Cool, so from here, all we have to do, I'm keeping both sides of the equal sign again, and I'm just going to expand on both sides. So EPG on the left-hand side, well, that's MGH, but it's my initial height, so I'm going to call it HI. EK, well, that's just 0.5 mv I squared, and I'm calling it VI because it's my initial speed. Then on the other side of things, as I start to expand and start to work downwards, I've got MGH, well that's just, or sorry, gravitational potential energy, that's just MGH, but HF, and I've got 0.5 mVF squared. Nice. Now again, it looks like we're running into that issue where mass is going to screw us over, but we don't actually need mass. So part of this is pretty mathy. If you remember factoring, this might help out a little bit, but if you could factor mass out of every single term, you can cross it off. So if I can factor mass out of this term, this term, this term, and this term, rearranging it, you would see how it crosses off. If you are not so familiar with factoring, don't worry about it too terribly much here. Just know if mass is exactly the same in every single term on both sides of the equation, or if anything's exactly the same on both sides, in every term on both sides of the equation, you can cross it off. So we'll cross off mass everywhere. If you have more questions about that, feel free to ask me, send me an email, or hop on a Google Meet, and we can absolutely check that out. I'm going to rewrite this again just without mass. So I've got G times HI plus 0.5 VI squared is equal to G times HF. I don't know why I made that F so big. It's supposed to be a subscript. F plus 0.5 VF squared. Okay, so what are we looking for? We're looking for VF squared. I'm clearly going to need to rearrange, and there's two ways that you could look at this. Maybe we'll do both ways actually. Why not? So the first way that a lot of people are going to choose is they're going to plug numbers in here. They're going to simplify as much as they possibly can, and then they're going to solve. So let's have a look at this. G is 9.81 times my initial height. I got to scroll back up and have a look. 8.6 meters. So 8.6. And then I'm going to add to that 0.5 times my initial speed squared. So that's 4.5 squared. That's going to be equal to 9.81 times my final height, which is 5.9 meters. I don't know why I'm starting to include units there, nowhere else, 5.9. And then we're going to add to that 0.5 times VF squared. Now as I go through and I want to simplify this, let me just grab the calculator there. I can go through, there we go. And on the left-hand side, I've got 9.81 times 8.6 plus 0.5 times 4.5 squared. Hit enter. So on this side, I've got 94 point, where did it go? 491. 491. And then on the other side, let's start to simplify this a little bit. 9.81 times 5.9. So 57.879 plus, because I haven't done anything with the 0.5 VF squared yet, so plus 0.5 VF squared. Okay, now what I want to do is, let's see, subtract 57.89879 from both sides of the equation. 79, so let's go back to the calculator, and let's do 94.491, and I'm going to subtract from that the answer from before, so 57.879. So that's going to be 36.612. And that's going to be equal to 0.5 VF squared. So I got to get rid of the 0.5 first. So let's divide both sides by 0.5. Just go back to the calculator. Divide by 0.5. 73 point whatever that says. And then I got VF squared. So I just need to take the square root of whatever answer that is. So I'm just going to go square root that answer. And we should end up with VF being, it's gone now, I think 2 sig digs, so 8.6 meters per second. Cool. So with this one, the way that we did it here is we plugged numbers in first and we simplified all of those numbers until we get to our final answer, which is VF. I'm going to take a split second just to show you the other way how to do this. So I'm going to erase from here. Hopefully I don't need to erase that final answer. And we'll show you what we're looking at. So in this case, we're looking for VF. Maybe I want to rearrange first. So I see that I am adding this entire term, GHF, so I might want to subtract that. So I've got G times HI plus 0.5 VI squared minus GHF is going to be equal to 0.5 VF squared. Cool. Still looking for VF. I can't really deal with the exponent until I deal with the 0.5, so I'm going to divide both sides of the equation by 0.5. So it's going to get rid of my 0.5. I need to get rid of the square root, so the last thing I do is take the square root of the entire huge thing, and then I can go through and I can plug in numbers for, just get rid of it like that, it's a little bit easier. Plug in numbers, so 9.81 times whatever that initial height was, 8.6, plus 0.5 times 4.5 squared minus 9.81 times, where'd it go? 5.9, there it is, 5.9. Then divide this whole entire thing by 0.5 and take the square root, when all is said and done, of the whole gigantic thing, and you'll never guess what it's going to work out to be. Go ahead and try and plug in the numbers. 8.6 meters per second. Now, when you're plugging the numbers in for this one, I would recommend, maybe I'll just show you here even, doing the entire top. So I do 9.81 times 8.6 plus 0.5 times 4.5 squared minus 9.81 times 5.9. So the entire top, hit enter, and then what it's showing us in the question over here is that entire thing is being divided by 0.5. So I need to divide that entire thing, which I've got now, which is 36.612. I'm going to divide that by 0.5, and then I'm going to take the square root of that answer, and it works out to be the exact same thing. Exact same thing. So perfect. Two different ways to do the same thing. Do whatever works best for you. If you like plugging in the numbers first, go for it. If you like rearranging first and then plugging numbers in after, go for it. Just make sure that you're doing things well and correctly. So little tricks either way. Now, one last, excuse me, one last little tiny thing to think about. Lots of people always ask me, let's highlight in green, doesn't the 0.5 cancel with the 0.5? And the answer is no. It's only, and we talked about that up here, it's only if the variable shows up exactly the same in every single term. So we've got mass, 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 mass in every single one of those four terms. It's going to cancel out. But the 0.5 only shows up in this term and this term. It does not cancel. Cool. So that's just showing my own work. I don't know why exactly I put that there. Everything after this is now enrichment. So if you want to stick around, I'll show you some of this. I'm going to go through it real quickly, real quickly. So I think this is technically example 3. But real quickly, lesson 6, same idea. It's enrichment. Lesson 6 is conservation of energy, but now we're adding friction force and work done by applied forces and things like that. So a little bit trickier. If you're good here, though, you can put the video on pause or stop or whatever and practice these particular questions out of your workbook, out of lesson 5, 1 to 3, 5, and 7. And we'll say goodbye for now. If you want to stick around, well, stick around. Let's jump into it. So the next example, and again, I'm not going to answer this one entirely necessarily, but we'll build a formula for it. So we got the maximum compression of a spring is 16.2 centimeters. Determine the initial height of the cart. So let's go through and let's just think, okay, ETI equals ETF, because once we set up our formula, it's not so bad. So initial, I'm going to call initial over here, and I'm going to call this final over here. So initially, it's at a height, so I've got gravitational potential. It's got some speed, so I've got kinetic. And then it's going to turn into, so at the maximum compression of the spring, that means when it's squished the most, it's not going to be moving. Kind of like maximum height, maximum compression means it stopped moving. So all we've got there is our spring potential energy. So when I start to expand on this one, it's mgh, I should put some little i's and f's next to these, mgh plus 0.5 mvi squared is equal to our spring potential energy formula, which you may remember that we looked at really extremely quickly from our last unit. It's 0.5 or 1/2 kx squared, where k is our spring constant measured in newtons per meter, so it is right there. So now all I'd really need to do is rearrange and solve for the initial height. We'll notice that mass is not in every single term here, so mass is not going to cancel out. Cool. So the reason this one's a bit of an extension is we're just adding that spring energy in at the end. Very, very good. So yeah, some space to work. And if you want to go ahead and try and solve this one, here is the work for it. So you can put the video on pause, you can check that out, you can compare it. Like I said, we're not going to spend a ton of time going through it, but if you want to, go wild. Okay, the next thing that's a bit of enrichment here, so if you flip to lesson 6, it's still conservation of energy. It's still ETI is equal to ETF. It's just for dealing with work done by a friction force or an applied force. I don't know why it just says friction, but it could be an applied force or some non-conservative force. So you remember at the beginning of the lesson, we had this and our total mechanical energy stayed the same. Well, if it's not conservative, the total mechanical energy is not going to stay the same. So for example, an extreme dirt biker, dirt biking up a hill at a constant speed. They're at a constant speed, so the kinetic energy isn't changing, but their gravitational definitely is. We've got these extreme, this is a very extreme lesson, by the way. We've got these extreme skydiving snowboarders who are skydiving and snowboarding. They've jumped out of a plane and now they are doing that. If they are falling at a constant speed, that means that they're losing gravitational potential energy, but their kinetic energy isn't changing. So they're just losing energy in this case. So the dirt biker is gaining some mechanical energy. The skydiving snowboarders are losing some mechanical energy. So here's the big thing that we looked at here. We've got our conservation of energy, which is our ETI equals our ETF. And that works for everything. That is just a very general conservation of energy. What we talked about last time, or in the previous lesson there, was that our initial mechanical energy is going to be equal to our final mechanical energy, and that's what we broke apart into kinetic and gravitational, and if you stuck around, spring. The thing that we're going to add to this now is the work done by any force. So the work done by any force, and we remember work done by any force is just FD cosine theta, right? So we can now figure that out, we can add it in. Here's the really, really, really important piece though. If it's adding energy, like an applied force, actually, let's see if I have this up here. No, skip that one. Skip that one. Gets to an example. Okay, whatever, we'll go back here and I'll just write it then. I thought I had it written out. So adding energy, for example, an applied force might add energy. Applied force. We're going to call it positive. So it's going to make our final energy bigger, right? So call it positive. Whereas if it's taking energy out of the system, taking energy out, so for example, friction forces or any resistive force, we're going to call it negative. So it's taking energy out of the system, or in other words, our final mechanical energy should be smaller. Cool. So if it's adding energy, like applied forces, call it positive. If it's taking energy out, like friction forces or any resistive force, air resistance, call it negative work. Cool. Okay, let's check it out in a quick example here. Okay, there we go. So a 4 kilogram box slides up a 7 meter long hill and reaches a maximum height of 5 meters. If its final speed is 12 meters per second, determine the average friction force. In other words, figure out magnitude of the friction force. Cool. So when I set this up, I'm going to say my total mechanical energy, and this comes from ETI equals ETF. So ETI is now coming from two places. It's my mechanical energy and the work. ETF is just my mechanical energy that's left over. When I expand on this, if it's at the bottom, the height is 0, so my mechanical energy is just the energy from the speed. In the end, at the maximum height, my kinetic energy is equal to 0, but I do have height, so my final mechanical energy is just gravitational potential energy, and then the work done always goes on the initial side, and it's the work done by the force of friction. Now we just mentioned that it should be a negative number, Now, if I don't put it as a negative number in my question, it's going to pop out as a negative number, and that's going to make sense. So as I go through, I kind of rearrange, and I might solve for my work done by force of friction. So my work done by the force of friction is going to be my gravitational minus my kinetic. So all I did was rearrange and solve for that. mgh minus 0.5 mv squared, that works out to be negative 91.8 joules. And the fact that it's negative, again, means that it's taking energy out of the system, which makes sense because it is a friction force, or work done by friction force in this case. But is work done by the friction force the same thing as the friction force? No. How can we get work done into friction force? Well, we say work done by the friction force is equal to the friction force times the distance. Now, what distance did it actually move? 7 meters, right? It slid 7 meters along the surface. So now that I know the work, I know the distance, I can rearrange and solve for that force. Cool. That's that one. And I believe there is one other example, but I'm kind of going to leave that one. Again, it's an extension. If you want to try it out, if you want to go for it, that's good. The big thing with that last example is you have work done by more than one force. So you've got friction force and you've got an applied force F. That's on page 134. So you would just, and actually, you know what? Maybe I'll do a split second with this. It'll only take a moment. Example 2. So we got ETI equals ETF. So at the beginning, if you're on page 134 looking at example 2, it says it's at rest and it's at 0 height. So we have 0 mechanical energy. So all we've got is the work done by the friction force plus the work done by the applied force, which we're just calling F. The work done by the friction force is negative, so I'm going to put a negative in front of it. It's taking energy out of the system. And then when all is said and done, we've got our final kinetic energy plus our gravitational potential energy. I know it's got kinetic because it's moving. I know it's got gravitational potential because it's got height. So if I could solve for the work done by my force F, then I could say the work done by force F is equal to that force times the distance, and then we're pretty much there. Okay, if you stuck around this far, good for you. It's you know, that probably means you're doing all right with physics. It's been really good talking with you, and we'll see you again soon. Bye for now, Physics 20s.